last time we finished off, we said, and I said I've got to come back to dative covalent bonding. It was something that I'd skipped over, right? So let's just have a look. It's a type of covalent bonding, but the difference, the eventual result is the same as a normal covalent bond. There's no difference between them, right? They're going to be identically the same. But what is actually happening in a dative covalent bond, all right, is we've got some examples that they give in various textbooks, but let's take, for example, what happens in here. NH3, ammonia, plus HCl gives us NH4Cl. Let's have a look what it looks like. We've got here NH3, right? N, and we've got H3s. So we've got an H there, we had an H there, we had an H there, and the rest was made up with, the rest was made up with our ammonia, right? Our ammonia over there, right? Because if we remember, okay, ammonia was a -3, okay? Let's have a look at it, actually the electrons. It's 1, 2, 3, 4, 5, 6, it's number 7. So it's 1s2, 2s2, 2p3, right? So if we draw the outside guys here, we can see that we've got 2s2, 2p3, that's 4, that's 7, right, which is where she is, and we can fill it. Now you can see that the electron structure around the center of the nitrogen, okay, there's 2 on the top and there's covalent bonds on the side, right? What actually happens when it forms this? We had chlorine, remember? Now chlorine was a little bit down, and on the chlorine side we had our, okay, and we had the hydrogen coming into the chlorine like that, right? What has happened here is that we have formed ammonium chloride. Well, how? What actually happened is that the hydrogen actually bonded, right? The chlorine took the electron away. The hydrogen has then bonded with the nitrogen's lone pair. So let's have a look what happened. Essentially it was this, okay? This hydrogen was left on its own. Its electron has gone to chlorine. The hydrogen, okay, was and what did it do? It came across and it shared on the side of the nitrogen. Okay, that's what's actually happened, right? It has formed in that way. Okay, so it's a dative covalent bond that has formed between those two. It's in essence, we just had here a proton and it shared the electrons with that lone pair over there, right? To form NH4 plus, because the NH3 wasn't charged, but the NH4 it's got an extra plus coming into it. The chlorine took its electron and it left. Let us have a look at the other ones. These are the ones that they normally refer to, is when we put HCl and water together, we form H3O plus and our Cl minus, right? How did this happen? Well, we had the chlorine as we had above, 1, 2, okay, like that, and over here, and we had the poor hydrogen guy over there, okay, and the H, what happens, the H2O, we had O, oxygen over there. Remember, we had the H and we had the H. Now what happened is the chlorine has gone off and become an ion on its own. So what happened to this hydrogen over here? Where did he go? This hydrogen split off and floated around as an H+. He actually came along and he linked into, and it doesn't matter which one you choose, he linked in to form H3O. And what does it look like? It looks quite simply like this. It's the same as the water, all right? Same as the water, oxygen. Let's put a hydrogen down there with that guy, and let's take our 2 across there, 2 across there. This H, okay, has come in over here. He's come in as a H plus and linked onto the lone pair over here. Okay? And you can also have O. And also, by the way, remember, sometimes we write HCl going to H plus and Cl minus. When we do this, right, we don't have protons floating around on their own. They actually link into the H2O to form the H3O plus. Remember? The proton moves across and forms H3O, 3O plus. So generally when we write that, we mean H3O plus. That's inferred. All right? Let's have a look at a different form of dative covalent bonding, okay? A different example, rather, okay? Is we've got, this is a different type of it. Boron. Now, this happens with boron and aluminium, okay? The same thing happens because they're in the same column, aren't they? Boron, if we look at it, it's 1, 2, 3, 4, it's 5. So it's 1s2, 2s2, 2p1, okay? So we have got 3 on the outside, haven't we? On our valency, okay, electrons, we've got 3. So we've got 1, 2, 3. Can you see that there over there, let's just do this in green, can you see over here there's nothing? These electrons here over here underneath, right? So in the outer shell, this area is electron deficient, right? It's deficient, which means that there is not enough electrons around the outside to form an octet structure, right? No matter what we do. Trifluoride, well, we know what happens there, right? Is fluorine comes along and fluorine links in here, a fluorine links in there, and a fluorine links in there, right? But this over here, okay, is essentially, it's deficient. So it doesn't do it necessarily, but it can now form a bond to fill that up, okay? And very often what happens is ammonia can come in there, right? Remember, ammonia is NH3, right? So ammonia has got the structure. Let's take, I'm just drawing it like this for a reason, okay? And let's put our red hydrogen, hydrogen, and hydrogen. But ammonia has also got these two here, hasn't it? Okay? Because it's got the -3, but it's full, right? So what happens is the ammonia comes and it sits in there. That is once again a dative covalent bond. Okay? Also called a coordinate bond. Okay? And it is shown, okay, a coordinate bond is shown in its structure, all right? There's a lot of these examples, all right? Essentially, what it does is it shows that the nitrogen has gone to the boron. So when we draw it, we would say B, okay, F, and the nitrogen H. That's how we draw it, showing that the nitrogen has gone to form the dative covalent bond, is shown with that arrow. It's gone to form it with the boron. So the nitrogen is using, okay, let's have a look what's actually happening, is the nitrogen is using these two to help boron to fill this gap. So it's also complete. All right? That's what the dative covalent bond is about. Now, let's go back to the molecular bonds, right? Let's have a look at originally we said to ourselves, remember we had the water issue, all right? Now, water is forming a hydrogen bond, right? Remember, we said we had we had H2O, we had an O over there, and an H. This was negative, this was positive. Along came another water molecule. The hydrogen happened to be that side over there, positive, and we had a bond forming between these two over here. That is a hydrogen bond. Right? That's a hydrogen bond between the two. Now, very often, okay, hydrogen forming with oxygen, fluorine, nitrogen, okay, those elements there, right, very often we get a polar molecule. Remember, this is polar, it's got a negative and a positive side, right? And there's the hydrogen on the positive side, okay? So, if it forms, let's say, for example, with nitrogen, all right, let us look what happens with nitrogen. We have N, H, 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 right? We have the three nitrogens out there. What happens here? Well, N and an H, let's have a look at the electronegativities of those guys. Okay, nitrogen is, let me see, is 3. And hydrogen is 2.1. Okay, so 3 minus 2.1 is 0.9. Difference in electronegativities, remember? And what does that mean? It is polar covalent, which means that the nitrogen side of the molecule over here is going to be, this is going to be positive, positive, positive side. The nitrogen is going to be the negative side. So it forms a polar molecule, right? So once again, in ammonia, when along comes another ammonia ion, all right, or another ammonia molecule, sorry, my thing, what happens here? Okay, the nitrogen comes along and it forms a hydrogen bond between the two, right, over there like that, right? So once again, we have hydrogen bonds formed, right? Okay. And similarly, we can do that with water, HCl, ammonia. Hydrogen fluoride is another one, HF. So when we've got hydrogen involved, what do? We look at the electronegativities, and remember, we look inside one loop at a time. Okay? So we looked at that loop first. Right, the electronegativity. That tells us how strongly that is being pulled, doesn't it? It tells us how unfair the electron time is. Too much electron time on the one side makes that side negative, right? Which means the higher the electronegativity, the more electron time. So these bonds here are formed between, let's say, a hydrogen and something else, all right? Now, they're actually a very strong bond, as bonds go, all right? And we're going to do a table of bond strengths now. And we're going to go through the different kinds and how they form. But what we've got is we've got this hydrogen bond, which is a strong bond, okay? Now, when we do the examples of this at the end, we're going to go through a table where we look at the hydrogen bond and why some of them... there's some anomalies that we look at when we look at things down the periodic table, which are explained by the hydrogen bond and the strength of the hydrogen bond. Okay, now, the most important part of this is to say to ourselves, okay, what is going on now with the next bit? Okay, the next bit is we're now going to look at these things forming together, all right? Now, this table, I'm not sure if it's in your textbooks or not, but I find it very useful to do so. Please feel free to copy it down and just maybe stick it in where this section is, because it refers to the bonds, the bond strengths, and where they sit relative to each other and how the things are formed. Okay? Let's have a look here. Let's take the top of the table. Oops, that's not supposed to be that. It's supposed to. Let's go back to black. So let's say, for example, we've got an ion and an ion. Hey, Kevin. An ion and an ion there, right? This is our sodium and chlorine, for example, table salt, right? This is a -1, this is a +1. Remember, electron time, no sharing, it's totally always on the ion, and it's got a delta electronegativity greater than 2.1. Right? Now underneath, right? Underneath we've got a dipole. Okay? Now let's see what happens when we form different compounds, right? Let's take, we have got a positive ion A, +1. Okay? Now this +1 charge is floating around in water, let's say. All right? And also in this water is an molecule CD. All right? Now let us say CD on its own is a dipole. And CD has got a negative charge here and a positive charge that side. What happens between those two? Let's look. Well, there is my CD, right? On the one side, I've got a negative, and on the other side, a positive charge. Okay? I am a dipole. I happen to come across an ion, which is a strong charge. So we will bond, won't we? Okay? We will, in fact, bond over there. Okay? There will be a bond between us. Because I'm negative this side and positive that side. The ion, remember, is a strong charge. Right? So this form of bonding here is called an ion dipole. And this is the order that we go down in. All right? This type of bond would be, for example, sodium hydroxide. Okay? Like that. Okay? Let's put the other sodium and the OH2, just leave that for a sec, right? So we've got that as an example, right? It's an ion with a dipole that is forming. It's in water, all right? Let us have a look at what else could happen. What else could go by each other? Well, we've got an ion going by a dipole. What happens if we have our trusty dipole over here, CD? This side is positive, this side is negative, and along comes a different dipole, EF. Right? Or the same dipole, or CD, all right? In fact, we can make it, let's make it the same dipole, shall we? It doesn't have to be, it could be a different one. Let's make it the same dipole over here. All right? And let's say CD. What happens here? Okay? In here, this is my negative side, this is my positive side, right? What happens between those two? Once again, I can get an attractive force between them, can't I? Because what have I got? I've got a positive and a negative side, a positive negative side, and I get my force of attraction between the two sides, right? That is called a dipole. Okay, sorry, black. This is called a dipole bond. Okay, now in between these two here, I'm going to put it in blue, is the hydrogen bond. All right, in between there is the hydrogen bond. We're going down strengths now, so we're getting weaker as we go down. All right, so you can see an ion can form with a dipole with a dipole, because there's a positive and a negative side. There's a positive and a negative of the ions as well. Well, what would be the next one? Okay, the next one going down in the list is what's called a ion-induced dipole. We've got ion A. It's a +1 charge. Okay, now it comes near, it's floating around minding its own business, and it comes near a pure, let's say, covalent bonded thing. Okay, this thing, the ion is so strong that what it does is In what was originally a nonpolar molecule, okay, what it does is it says, hold on, this was, let's say, I don't know, let's say C and C. Two are the same, which means it wasn't polar. It's pure covalent, right? What did this do? This was so positive here. What did the poor electron do? The positive pulled the electron that was being shared, remember? Pure covalent is a pure sharing of electrons. There's no more electron time on one side. The positive over here pulled the electron to the side here. So what did it do? It made this go negative and this go positive. So that ion pulled the electron towards it. It was positive. It created a dipole, didn't it? So what do we call that? We call that an ion-induced dipole. Okay? The ion made a dipole and then bonded with it, because now it's actually pulled the electron that side strongly, so we can get that. Okay? The next one is fairly straightforward. If you think about the sequence, we've got our good friend CD again. Okay? CD is a dipole. C was negative, D was positive, right? Let's take this next to something that was uncharged. Okay? What happens here? The same as happened above. It's just the dipole is doing what the ion did last time. So over here, the positive, it starts to attract the electrons to this side, doesn't it? Meaning this becomes negative, that becomes positive, so we've got an induced dipole, all right? And if we like, we can call that E and E, all right? It's made a dipole out of this. It could just have been E, a single atom on its own. In fact, let's just make it E on its own. Look, it's pulled the electron to the side, hasn't it? So it's created a dipole. So what have we got here? We've got a dipole, induced dipole. Okay? We've got a dipole, induced dipole, right? And the last one of them is called the dispersion. Oops, sorry, I put it in the wrong place here. Okay, it's called the dispersion or London forces. Okay, basically what is that is when we've got, it's a very weak force. Okay, what happens is we get an out of balance. We've got two elements, right, over here, two atoms, two molecules, two whatever. Okay, and what we get is we get a temporary situation where this side goes positive, that side goes negative, and this side then goes positive, and that side goes negative, right? Creating a force of attraction between these over here. That one was over there, right? So those are the system of forces that we've got. Starting from the ion at the top, which is the strong ones. Remember, we could have Mg plus 2, two full protons. Now, in the scheme of things, right, those two protons or the two electrons, they are the battleships. They're the heavy charged. They come through with this huge charge. They can do a lot of linking in with other things. They're so strong they even make dipoles. Okay? They pull the electron towards them or push it away. So if we had a very strong, for example, chlorine, very strong, very electronegative, it hangs onto its electrons with absolute tenacity. Chlorine is a negative ion. What happens? Chlorine is in the water. It comes by this poor unsuspecting thing. This is so negative, it pushes the electrons to the side. Right? So it pushes the electrons that way, doesn't it? Pushes them away, leaving the proton over here I should probably use what I've always used and be red. Okay, but it leaves the proton uncovered. It's positive this side now, and it allows an bond because the negative links to the positive. So essentially it pushes the electrons out of the way so it can get a linkage to the proton. Vice versa, if a proton comes by, it pulls the electrons in because that's what it wants to link with, right? So those are the forces that we've got, okay? Now, you'll hear the words van der Waals forces, okay? Here they are. These all here are van der Waals. From the dipole down, right down are all van der Waals forces. To give you an example, they're pretty much less than about 20 kilojoules of energy per mole. They're not very strong, right? So they're easy to break apart, and in breaking apart, you're not probably going to break apart the inside of the molecule itself either. Okay? And then the energy of, for example, an ion dipole and a hydrogen bond is 40 kilojoules per mole and above. Okay? So that's the type of forces that can hold actual molecules together. That is why when we drink a cup of water, we've got the hydrogen bonds keeping them together, right? And there's quite a lot of theory in there that you've got to go through, unfortunately, with, where we've got to remember certain sort of topics, right? One of the things that's usually sort of asked in this is they will take and they'll give us a curve. I just want to look at it like this. This is 100 here. All right? And they say, this is H2O. Okay, that's a very poor H2O. This is 100 degrees Celsius, is H2O. That's the boiling point of water. And then down here, they give you H2S and H2SE, H2SE, and H2TE. Okay? Now, they want to know, they say to you, but hold on. If you look at the periodic table, okay? Have a look at the periodic table when you're doing this one, right? You will see that we've got oxygen, sulfur, H2S, right, which is the bottom one over here. Let me put it in there. It doesn't look right down there, okay? H2S, you've got oxygen, sulfur, selenium and tellurium, and polonium below it, right? Now, we know that if we look at, let us take let's just look at it, right? If we look at oxygen, it's yay big, right? If we look at sulfur, it's yay big. If we look at selenium, tellurium, why? Because we're adding protons, neutrons, and electrons. We're making a bigger atom, aren't we? Right? So the atomic radius is going up, and this is against the atomic boiling point, against the atomic mass. Okay? Against the atomic mass. So what would we expect? We would say that if we look at this logically, we would expect, okay, water to be down here somewhere. All these others, can you see, this is my atomic mass going up here. It's increasing as I go along. So I would expect the water has got the lowest, H2O has got the lowest atomic mass of all of these. And yes, I would expect the boiling point to rise. Why? It's just they're heavier molecules. I've got to put more energy in to get them moving along, haven't I? Right? Just thinking about it like that, just on a casual way of let's putting it. We've got to put more energy in to get these guys moving. Water should be down here. It's light. But it's not. It's high. Why? What has caused this? The cause of it is the hydrogen bond. Okay, the strong hydrogen bond in water, remember, let's just page down. The hydrogen bond in water, right, is, that was dative covalent, is up here. It's in the middle here. Okay, it's almost at an ion dipole. It's a strong bond. Therefore, it's an anomaly. Because to get the water to boil, I have to change the hydrogen bond. I have to break a hydrogen bond, which takes a lot of energy to do it. Okay, you will also see on the table not only those, very often they put in these as well, right? Let's have a look at this one. HF, HCl. Okay, HCl. Then it goes HBr and HI. Okay, can you see it's the same kind of pattern, isn't it? What is happening here? Essentially what is happening there is purely the hydrogen bond. The HF is more electronegative, it's stronger polar, thus leading to hydrogen bonding than the HCl and the HBr and the HI. Okay? That's what is happening with those there. Similarly, the last one of all that you see ammonia on it as well. Let's just put that in blue. Over here, you will see NH3. Just do this. You'll see NH3 over there, and coming down over here, you'll then see, now what is below it? pH3. And over there is H3AS. And possibly bismuth, BiH3, right? You'll see the same sort of thing occurring like that. Okay, that is, once again, it's the hydrogen bond that is causing this. All right. So next time we're going to move on and we're going to start looking at the gases, the gas laws. That's going to be the next section that we're going to deal with. A very nice section, and then I'm going to come back and start putting in some examples in here, because I wanted to get through the theory before we start looking at the examples. So as I say, next time, that's what we're going to be doing.